Hello and welcome again to another edition of Lost in Science. This is half an hour of sciencey radio across Australia on the Community Radio Network. If you were listening last week, you would have heard us talking about the Ignobel Prizes. We're back again this week with the real thing, the real deal, the Nobel Prizes. I'm Stu. With me I have Chris, who has an issue with the Nobel Prizes.
I do. They're not as fun, I got to say. Would you agree, Claire? Because you're also here.
Yeah, I mean, yes, hello, everyone. And look, for what it's worth, it would have been better to do it the other way around. We had all this fun last week with the Ignobels, and now the groundbreaking, life-changing science that we're going to talk about today. Grown.
Look, maybe we should pen a sternly worded letter to the Nobel Committee and ask them to move the Nobel Prizes to before the Ig Nobel Prizes in future, just so we can have a few yucks afterwards. But probably unlikely that they'll pay any attention to us whatsoever. But we are going to be talking about the Nobel Prizes, the sciencey ones. Were announced last week, a day at a time. They do it that way for some reason, I guess, so that media have more column inches to write each day or something, so they don't jam it all into one story. Anyway, the Physics Prize was announced, and Chris, you're going to be talking about the Physics Prize. What are you going to be telling us?
It's actually a very fitting one this year. It's probably the reason why they gave it to these people. It's a quantum achievement. It's quantum technology. In fact, it's groundbreaking quantum technology. Some would say, pioneering. So I can see why they go. I can see why they awarded to these people.
Do you think they pay any attention to that it's the International Year of Quantum?
Surely.
Yeah. I think it's rigged.
Yeah. Okay. Right. I mean, I always do wonder, how do they choose? Because as we said the other day, these prizes aren't necessarily for work that was done in the last year. It's not like an annual prize in that way. So yeah, I do wonder how they choose. It's these guys' turn or something. Anyway, Claire, you're going to be telling us about the medicine prize.
Yes, the medicine or physiology, whatever you want to call it, and three very deserving scientists, research scientists who did some amazing work discovering a new immune cell and working out how our bodies, work out whether cells are us or whether our cells are invaders and pathogens, because it's a very complicated system, and it can lead to things like autoimmune diseases, or it can, if you have a system that doesn't recognize self from non-self, or is then you can also get cancer growths, which so it's a very it was a discovery back in the 90s for these three scientists, and they're finally getting the recognition. It sort of spawned this whole sort of new area of immunotherapy as well. So awesome.
Cool. And I am going to be talking about the Chemistry Prize, which is awarded to three people for work in coming up with some new chemistry stuff. But it's probably easier if I explain that in the story. So let's just get on with the show.
Yes, you are listening to Lost in Science on Nobel Week, I guess we could call it, is our celebration of Nobel Week. And I'm going to be talking about, predictably enough, going to be talking about the Physics Prize, because that's, pigeonholed, I guess, typecast.
Yeah, I mean, it's also a quantum physics prize.
It is a quantum physics prize, and I feel like I'm contractually obligated to talk about quantum physics and particularly quantum technology as much as possible this year of quantum.
Indeed.
Exactly. So, yeah, look, diving in, this is the Nobel Prize was awarded to 3 physicists, John Clark, not that Clark, John Clark, different John Clark, Michael H. Devoret and John M. Martinez for their work in, well, I won't read out the full title because that's just something, there's about macroscopic quantum effects, essentially. So, and quantum tunneling in particular. All right, so we all know, we've talked about quantum physics a lot so far this year. We all know that quantum stuff happens at very small scales. That's right, isn't it?
Yeah.
Like it's atoms and the like.
Subatomic.
Yeah. Okay.
Yeah. Yes.
You were asking a question. I thought you were asking a question.
Yes. No.
Okay. And so and so this is about trying to find an effect that's a bit larger than just at the scale of a single atom or a single electron or this sort of thing. And so what they're doing is particularly looking at the phenomenon of quantum tunneling. And this is something that you get with quantum systems. It's like if you have a quantum particle like an electron, something like that, that comes up against a barrier, like a wall or something, then there is a non-zero. It's sort of probability distribution where it could be can stretch out, be non-zero beyond the barrier, and so the electron has a chance of jumping through the barrier and appearing on the other side. This is something that can't happen in classical physics. Things just don't jump through walls, but in quantum physics that can happen because a particle is kind of spread out in space with the probability of where you can find it, and that can go through these barriers. It is something that is used at the scale of single electrons when you talk about things like electron microscopes, which involve having a very kind of fine probe that hovers above a material, and the electrons can jump the gap between the probe and the material, and that's how you see things with an electron microscope effectively. But that is on the scale of single electrons. This prize was awarded for doing it with a whole lot of electrons, basically a electric current. So this is experiments that was done in 1985 on superconductors. So, and because this effect, they got to happen, it was theorized to happen with superconductors, but they had to, had these special arrangements of superconductors at very, very low temperatures. We're talking thousandths of a degree, like millikelvin, so thousands of a degree above absolute zero. So really, really, basically as cold as you can get. And so what they had is something that is, the name for it is it's called a Josephson junction, which is basically where you have two conductors separated by an insulator. And again, from the classical kind of thing, electric currents can't go through insulators. But in the quantum effect, you can actually get the electrons, if they're all in the right quantum state, they can jump across the insulator gap, and you can get a current pass between the two superconductors. And that was theorized, at least. That was in the 60s, that theory was written down. And these physicists in the 1980s, they managed to build this thing and, show that this quantum effect was actually real. And it's, as I described it, it doesn't sound like very impressive because it is like a, thousandths of a degree above absolute zero, and it's with special materials, that sort of thing. But it's useful because it is actually using quantum effects in, like I said, an electrical circuit with actual electric currents that you can measure. As I said in some of the announcements of this prize, it's a device you can hold in the palm of your hand. Like, it's big enough to be like visible. It's not microscopic. It's an actual macroscopic thing that you can hold in your hand and say, this is acting with quantum behavior. And it's the kind of thing that has set up the possibility for the quantum technologies that we are celebrating in the year of quantum. So things like quantum computers, a lot of them work on superconducting systems, and they take advantage of these quantum effects in electrical circuits to bring us quantum computers. So this is kind of the first, I suppose, realization of this quantum technology in a practical sense that could then be used to make this kind of technology. So yeah, that's essentially the significance of it.
But so this work was done in the 80s.
Yeah.
You say that they actually show this. So these guys have been just sitting around waiting for a Nobel Prize since then, or been doing other work?
Well, like as we discussed in the intro, I think because it's the year of quantum science and technology, they probably tried to look for a quantum technology Nobel Prize to give out. And this being like the first big achievement in quantum technology, it makes sense that they would award it to them. But yeah, I don't know. I mean, it's kind of one that I don't think was on any of the bingo cards that anyone was seeing this happening as being recognized for a Nobel. But yeah, it's a kind of thing that as the technology becomes more realistic, like the quantum computers, quantum cryptography, those sort of things, as they become more practical, then you kind of have to acknowledge retrospectively the people who started it all. And I think, yeah, that's how it's come about in that sense. I don't think when they did the work, they went, "Ooh, Nobel Prize," automatically.
I guess it meant the importance of it isn't necessarily immediately apparent when someone makes a discovery like this. People in the quantum physics world probably went, "Oh, that's really interesting," but until it has an application that will affect, the majority of people, it probably doesn't get as much attention as it deserves, possibly.
Yeah, and particularly at the time when superconductors were still, there's a lot of work being done on them, but they were seeing this future technology, this thing that wasn't quite there yet. It was very much a laboratory thing that wasn't affecting anybody's daily lives. But yeah, we're a long way now. That was 85, like I said, that's like 40 years ago. Things have changed a lot, and we'll still get to see the promise of some of this, the real our lives changing due to quantum computing, etc. But it's now real, so it's worth acknowledging.
Across Australia on the Community Radio Network, you are listening to Lost in Science.
So the Nobel Prize for Medicine or Physiology was also announced recently, and this year it went to 3 scientists, one from Osaka, Shimon Sakaguchi, and 2 from the States, Mary Brunkow and Fred Ramsdell. Fred apparently was in the wilderness off-grid and didn't know he'd even got it, which is, I really love that. And apparently Mary's dog was like attacking the people who were like trying to tell her that she'd won a Nobel Prize as well. So it really suggests to me that they really have no idea that it's going to happen and that they're going to win this giant prize of their whole careers. Anyway, that's an aside. So these 3 researchers had a breakthrough and discovered a new immune cell, and pretty much a whole new way of understanding how our immune system works and the possibilities of us being able to manipulate our immune system and coming up with new ways to fight disease. So, sounds pretty impressive, huh? So to explain a bit more from the start, let's start with the immune system and the question of how does our immune system recognize our own cells and how does it recognize other cells? Because it does perform this very delicate act. It protects us from thousands of disease-causing pathogens on a daily basis, but it keeps in check and it doesn't go around by and large killing our cells. So most of the time it does a job of this, but there are diseases where our immune system can go into can go into
overdrive.
Overdrive, that's the word I'm looking at. Can go into overdrive. And you've got autoimmune diseases such as type 1 diabetes, lupus, and rheumatoid arthritis that happen when your immune system pretty much mistakes your own cells as a threat and then attacks them. So the discovery from Sakaguchi, Brunkow, and Ramsdell really drills down into how your immune system balances this. And there are 2 main discoveries that this is about. So one is the discovery of this cell called these regulatory T cells or Tregs or Tregs maybe. I don't know if anyone calls them that. I think Tregs is good. Yeah. Tregs is good. And also the discovery of something called the FOXP3 gene, which is linked to these cells. So back in 1995, Sakaguchi from Osaka discovered this new class of immune cells called the regulatory T cells or Tregs. Little dinosaur hands for those listening, which actually revealed that in our immune system we have an additional immune layer of protection. So these Tregs give us a peripheral tolerance. They act as security guards of the immune system, and they pretty much like patrol the body and they'll suppress any rogue immune responses, any rogue immune cells that could go out and attack and kill any of our own cells.
Oh, so they don't target invaders. They target
they
watch the Watchmen.
Rogue immune cells. Yes, they watch the Watchmen. Yeah.
They're like military police.
Yeah. Exactly. So any of these cells that could potentially lead to autoimmune disease, that's the ones that these Tregs are keeping an eye out for, watching the Watchmen. Watch people, I think. So yes, Sakaguchi identified these cells, and then in 2001, Brunkow and Ramsdell figured out how they're controlled. So they did this by looking at mutations in this gene called FOXP3, and when this gene had a mutation in mice, it gave this fatal autoimmune disorder, and then they showed that there's a similar that there's a similar autoimmune disorder in humans called IPEX syndrome. So if there's a mutation in this FOXP3 gene in humans, then you have a similar autoimmune issue. So then comes and then Sakaguchi comes back in 2003 and he confirms that FOXP3 is essential for the development of regulatory T cells, our Tregs, and that the FOXP3 codes for a type of protein called a transcription factor, which turns on genes necessary for the regulatory T function. So yeah, these Tregs can be good guys, they can be bad guys. When they work or they don't work, they can lead to autoimmune diseases. But on the other hand, they can work too well. So they can be too effective in suppressing immune responses that might otherwise destroy cancer tumours.
Perfect, because I thought of another analogy, this Jurassic Park, where you had the velociraptors were attacking everybody and the T-Rex, spoilers, came in and saved people from the velociraptors. But the T-Rex themselves could be a risk, a threat.
That's right. Well, I don't know if these T-Regs themselves are a threat, though. Okay. So I'm sorry. I mean, I think we're going to have to look into this analogy a little bit more. Is all I'm saying. Yeah. So yeah, why the Nobel Prize? Well, this understanding of the Tregs and the FOXP3, it's really launched this new era in immunotherapies to sort of harness the immune system to treat autoimmune diseases and cancer. So they're potentially looking at ways to boost the function of Tregs to be able to figure out ways to treat autoimmune diseases, and then for cancer, the goal is to inhibit the Tregs and allow the immune system to target tumours more aggressively. So yeah, great work to all the researchers, and
sounds like they deserve a Nobel Prize.
I think they might.
Across Australia on the Community Radio Network, you're listening to Lost in Science.
All right, when we think of chemistry, most people likely think of a classic laboratory setup with bubbling liquids and mysterious vapours and various glassware and Bunsen burners. And that image might well have been what you expect to see in a chemist lab in the 19th century and possibly the early 20th century. But chemistry is a lot more than just adding things together and see what goes boom. So I know, don't give me that look, Chris. It's not physics, but it is physics. The Nobel Prize for Chemistry this year has been awarded to three people. Susumu Kitagawa, a professor at Kyoto University, Richard Robson, a professor at the University of Melbourne, and Omar M. Yagi, a professor at the University of California at Berkeley, for their work in the development of metal organic frameworks. And if you immediately thought of the Terminator from Terminator, you couldn't be further from the mark. It's really nothing like a cyborg with living and synthetic components. This is one of those times where organic chemistry has got nothing to do with life. It's got to do with basically chemicals that have carbon in them.
Right.
So
again, not as much fun as the Ig Nobel.
So you're telling us that things can be organic and still have chemicals?
Well, there definitely are chemicals in everything organic, yes. But organic chemistry has got nothing to do with living things necessarily. That aside, this is not how most people think about chemistry, but when we talk about chemicals, most people think of liquids and powders and gases and how they might be combined to form new compounds or new molecules. And these kind of simple chemical reactions are relatively easy to understand. There's a fair bit of maths involved. If anyone remembers back to doing chemistry in school, there's lots of balancing equations of chemical reactions and figuring out where things go. That's actually the basis of this prize, to be honest, is people sitting down and working out on paper what would happen when they combine certain things in certain ways. So, in organic chemistry and biochemistry, simple compounds are combined to form even more complex compounds like polymers, which usually take the form of a string or a chain of monomers which are joined together. There's strings of polymers. But the work recognised in this year's Nobel Prize is looking at fully three-dimensional compounds which have chemical properties that make them useful for tasks which more traditional chemical reactions are less practical to achieve. So Richard Robson, who is the professor at Melbourne University, did some founding work on metal organic frameworks back in the 1980s. Again, this is quite an old bit of work that he's being recognised for. Apparently you've all seen those models of atoms and molecules with wooden balls, and they're joined together by sticks to make the chemical structure.
Yeah, sure.
So he was given the job of making those models for students at the University of Melbourne, and he realised that the angles that you put the holes into the balls influence the way the models fit together, and he realised that was how molecules fit together in reality, and worked out that if you worked out the angles properly, you could work out the shape of the molecules they would make, and therefore you could work out 3D shapes of things that you could make out of these chemicals. It's a real jump in theoretical thinking, I think. It'd be great if we could get Richard on the show sometime, but as he said when he found out he won the prize, he's 88 and he's not prepared to deal with the all of the consequences of winning the Nobel Prize at his age. However, what he did was combined a copper ion and an organic nitrile compound to bind them into forming a complex crystalline structure with regular diamond-shaped cavities. So other molecules or other atoms, other things can be trapped in those cavities in the 3D substance. It's like a 3D lattice work through which other materials like gases or liquids can pass in a very predictable and repeatable pattern, and the lattice can be manipulated to hold things in those cavities in the structure. So his early models were not very stable. They deteriorated rapidly after formation. Other researchers, including Kitagawa and Yagi, took up the challenge.
So say the early models.
And developed
the early ones, you mean the ones out of wood and the balls?
No, the early metal organic frameworks he made just deteriorated really quickly. The wooden models are probably still at the University of Melbourne, I'll be honest. They're still in the classroom there. But so these guys, they developed more stable frameworks. No one really thought much of their work, so they kept publishing these papers, and people said, what's the point? There were materials that chemists and people were using which had similar properties. There's a substance called zeolite, which we have access to, which can do this kind of thing. And they went, why would we want something that's not even stable? We've already got zeolite. We don't need to do this stuff with a new substance. But what they worked out was that you can, because you're constructing these frameworks and you're working out how they fit together, you can tailor them for specific purposes. And they can be used to perform as chemical catalysts. So some of the potential uses for these metal organic frameworks include things like separating PFAS from water.
Wow.
So you pass the water through the metal organic framework, the PFAS all gets stuck in the gaps in the lattice work, and the water passes through and it's clean.
Oh, amazing.
Potentially filtering greenhouse gases from the atmosphere in an efficient and scalable way. So you basically just push the air through, the carbon gets trapped, and the air goes on through the framework. Can also be potentially used to condense water out of air, and has been demonstrated to do this in the desert. They've actually got a framework that can get this, and it's to do with temperature gradients. So overnight, water condenses in the gaps in the metal organic framework, and when the sun heats it up in the morning, the water all drops out, and you get water. So that could be used in deserts and on other planets. Can be used to capture and store toxic gases. Can be used to capture ethylene from ripening fruit and slow down the ripening process to extend shelf life. So these chemical structures have enormous potential, and like I said, I could probably spend a whole show talking about how they were discovered and what they could be used for. But honestly, if you want to know more, please have a look at the Nobel website. There's a whole bunch of further information and background stories on how these got discovered, but definitely a useful thing. Not fun, but definitely interesting. And that is all we have time for this week on Lost in Science. Thank you for joining us in Getting Lost. If you have any questions or suggestions for the team, get in touch with us by email. We are lostinsci@gmail.com. You can send cheap tweets to us at LostInScience1 on Twitter, or you can find us on the ubiquitous Facebook. Lost in Science is recorded at the studios of 3CR in Melbourne on the land of the Kulin Nation, and is broadcast across Australia on the Community Radio Network with the assistance of the Community Broadcasting Foundation. You can find a podcast version of the show on 3cr.org.au, or you can tune in the way you did this week when we return in our usual time slot to get Lost in Science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.